Okay, we are taking a look at the second part of lesson 2, which is lowest common multiple. So we see the list of multiples. These are written as lists. If we create a set, the only difference for a set is we use curvy brackets. Those are called braces. That's the only difference if I were to make a set of multiples versus a list. So these are lists. So they're saying the multiples of 6 are 6, 12, 18, 24, 30, 36, 42, 48. And the multiples of 8, 8, 16, 24, 32, 40, 48. Then it's got a 5. Well, it meant to say, what would that be? What do you think? The 5 doesn't go there. What number should be next? They're missing a number. It should be 56. There we go. It should be 56 and then ... Sometimes the book is missing some of the answers, and sometimes the answers in your answer section are wrong. We have had a few of those instances. So we try to take a look at those, and then we email the company so they can fix them. Okay, so we're talking about common multiples. So if we want common multiples, that means they have to show up in both lists. So far I've got a 24 and a 48. Now we want the lowest, the least. So the lowest common multiple here is 24. It's the lower, smaller number. All right. Now, again, if I wanted to check that on my calculator, what would I do? Who remembers what to push on your calculator to do that? How do I get that GCD up? Math across to number. So use your right arrow across to number, and then it's number 9. Number 9, you're going to see, or is it, that's greatest common denominator. Oh, hang on. That's your greatest common denominator. Hang on. That's not the one I want. I want LCM. Math, number 8. There we go. LCM. So now if I put in 24, 48, I'm going to get, whoopsie. Why did it give me 48? Oh, because I used the wrong numbers.
LCM 6 and 8.
Right. LCM 6 and 8. All right. Number 8. 6, 8. There we go. We're going to get 24. So you got your LCM in there, and then you got we have our GCF one. The GCF one is the GCD. So we are looking for greatest common factors, and then we look for the lowest common multiples. Now, yes, we have to do it longhand because we're going to be comparing more than 2 numbers quite often. For example, if we look at the next example, it says 5 and 7. So what we would do is we could create lists by counting. It's called skip counting. So that means for 5, I would count by 5s. 5, 10, 15, 20, and so on. But the rule is, if you've got a list of numbers and you're comparing them, start with the larger number. So I'm just going to do 7 right above it. So 7 becomes 7, count by 7s now. Add 7 more. 14, add 7 more. 21, add 7 more. Whoopsie, 28. Add 7 more, 35. And we're going to notice that with the 5, I'm going to get 25, 30, 35. We're going to end up finding our 35. So start with the larger number. You're going to take the smaller number a long ways in order to find the larger number, but do the first 5 of the big number, and then you'll find the smaller number quicker. So this guy, his answer would end up being 35. Now we've got 3 numbers. So for 3 numbers, again, you're going to make a list. So if I've got the number 10, I'm going to count by 10s. I've got the number 15, count by 15s, and the number 20. 20 is the largest, so I'm going to count by 20s. So 20, whoa. Why are you glitching already? We just started. Come on, computer. So 20, 40, 60, 80, and 100. So I did the first 5 of the larger one. Now I go to the next larger one. So my first one would be 15, 30, 45, 60, 75. So far, I've found 60 works. So far, 60 is in common with those two. Can I make a 10 become 60? Yes. So I can go 10, 20, 30, 40, 50, and 60. So we're going to notice that now I do come up with my common number. I found 60 in all the lists. So my common is 60 for B. Now I've got the numbers 10, 12, and 14. They're all even numbers. Does that change things? No, we're still going to do the same process. Now, what's another way to create multiples? Another way to create multiples instead of skip counting is to times by 1, times by 2, times by 3, times by 4. And you're multiplying the original number each time. So, for example, I'm going to start with the number 14. So if I go 14 times 1, 14 times 2, 14 times 3, 14 times 4, and 14 times 5. You always do 5 of the larger number. Okay, first one's going to be 14, then 28, then 42, then 56. Oh, what's that going to be? 70, I think? Yep. Okay. Now we're going to do the numbers 12 and then 10 we know can get there. We need to have a 0 in our number because 10, if we're counting by tens, the numbers only end in zeros. So you're going to notice here, I made sure that I got to a number that ends in a 0 because that's what's going to happen to my tens. I'm going to go 10, 20, 30, 40, 50, 60, 70. I'll get to 70. But let's see if 12 gets to 70. I'm not sure it does. We might have to go larger. And sometimes you do, and that's okay. This one, we're going to have to go very large. We're going to notice that the only number that's actually going to work, it's huge, is 420. So we would have to make very large lists here. Okay, so 12 wouldn't work. So I could get between 10 and 14. Between 10 and 14, 70 would work. But the minute I throw a third number in there, the number 12, that throws off my numbers. So now I need to find something they have in common. So that means I have to keep listing numbers until I find one that they have in common. And that would have been big lists, but that would be what we have to do. And we would get 420 for that question. All right, so it says, in this example, the first two were quite easy to do. This one was quite hard to do. The reason he was quite hard to do is because he's a huge number. So is there another way we could do this? Yes, we're going to use our prime factorization. Because if we use the prime factorization, the prime numbers that they have in common, we can find the lowest common multiple very easy. So if we take a look, 10, what are the prime numbers that 10 breaks down into? Well, if I were to make a factor tree of the number 10, I would have 2 times 5. And same with 12. If I broke 12 down, I would have 2 times 6, and I would break 6 down into 2 times 3. 14 would break down only to 2 times 7. So what have we done? We have found the ones that are different in each of them. So which ones do they have that are different? So first of all, we take the prime factors of one of the numbers and we add the additional ones. So my smaller number, okay, so I would take this number. My prime factors are 2 and 5. So we're taking the 2 and 5 from the number 10. So that's where those two numbers come from. Now I'm going to look at the number 12. 12 broke out into 2 times 2 times 3. Well, the number they have in common is a 2. I need to take the other different numbers. Well, the other different numbers are 2 and 3. So I had to use the numbers 2 and 3 from the number 12. And what is different in the number 14? Well, 2 is in common with all of them. The only other different number is a 7. So I would use the 7. Okay? So that's where we get all of our numbers. And now if I multiply all those numbers, I'm going to get 420. So it gets to the answer a heck of a lot quicker than me making those skip count lists or those multiplying lists that take forever. Holy cow, that is glitching hardcore here. Let's try that again. There we go. Okay, turn your page. We'll do some more examples and see how this works actually. So now we're going to prime factorize 15 and 35. And I'm going to do it using the factor chart. So I'm going to use 15, ends in a 5, divides by 5, gives me a 3. 3 divides by 3 to give me a 1. My prime factors are 5 and 3. So I would say 15 equals 5. Well, start with the smaller number, pardon me. 3 times 5. And then we get 35. So I'm going to make a factor chart, or a division table, pardon me, of 35. Again, this one ends in 5. So I'm going to divide by a 5. Well, that's going to give me a 7. And then I'm going to divide that guy by a 7 and get my 1. So now, again, my prime numbers are on the left-hand side. So now I know this guy breaks up into 5 times 7. Now, what do we have to think about for this question? You're trying to take the least amount of each number that you've got. So each separate number. Well, I've only got 1 3, so I've got to use a 3. I've got 2 5s, which means I use one of them. And I have 1 7, so I have to use the 7. So my LCM is going to be 3 times 5 times 7. This is the one they have in common. There's 2 of them. We take the least amount. Okay, we use the least amount of them. So that means there's only 1 of them. And we multiply that out. That's going to give us an LCM of 105. Okay, whoa. I'm not sure why this is glitching so much today. Every day it does this. Okay, next question. 126 and 441. Again, I'm going to use a division table to save room. I'm going to take 126. It's an even number. Even numbers divide by 2. 126 cut in half is going to give me 63. 63 is an odd number. Odd numbers we start dividing by 3. And yes, he will divide by 3. Come on. There we go. And that's going to give me 21. And again, it's an odd number, so I'm going to divide by 3. And that's going to give me a 7, which I'm going to divide by 7 to give me a 1. So for 126, I'm going to list my numbers in a moment here. So I get 126 equals 2 times 3 times 3 times 7. And now we're going to do 441. Okay, 441. It's an odd number. So dealing with an odd number, come on, you silly machine. We're going to divide it by 3. And it will divide by 3 147 times. And that's an odd number, which will divide by 3 again, which will become 49, which we know is a perfect square. So that's going to divide by 7. And it's going to leave you a 7, which will divide by 7 again. to leave us a 1. So now my prime numbers for 441 are 3 times 3 times 7 times 7. All right. So now what we've got to do is we've got to take our LCM. So which numbers are we going to use? Well, for the number 2's, how many number 2's do we have? We have 1 of them, so I have to use it. So let me just write my LCM down here. So LCM, and this is for this question here. So we know we have to use the 2. Now we've got 2 3's in each number. That means I have to use both 3's. Okay, and now I take a look at how many 7's I've got. So 7's, I've got minimum 1 7, but I need to take the maximum amount. So I'm going to use both 7's. And we're going to write a little rule for this in a moment. So that's going to give us 882. Huge number. And could you imagine the list we would have had to draw for each of those numbers to get to that? That would have been big lists. So this is saving us a lot of time and room. Okay, now we've got 3 numbers. Now, could I have put those 2 numbers in my calculator to solve it? Yeah, I could have. But remember, you're going to find questions on your quizzes and tests where it says, Jim did the question over here, Sue did the question over here. Where did they make a mistake? Who made a mistake and where? Okay, so you have to know how to do all the questions longhand. All right, number 22. All right, 22 is an even number. What does he divide by? 2. To give us an 11. An 11 will divide by itself and give us a 1. So my numbers for 22, I'll just put it right here. 2 times 11. Okay, and now I'm going to do 154. That looks like an 8. One, 5, 4. Okay, it's an even number as we can see. So we are going to divide it by 2. So we're going to cut that sucker in half and we're going to get 77. And we know that number will divide by a 7. And it'll leave us an 11, which divides by itself, 11, to leave us a 1. So 154 is 2 times 7 times 11. And our third number, 198. Oh boy. Okay, we're going to do a division table with this guy. He's an even number. So we're going to divide him by 2. And that's going to give us 99, which divides by 3 to give us 33, which also divides by 3 to give us an 11, which will divide by itself, 11, to give us a 1. So we get 2, come on now, 2 times 3 times 3. Boy, this takes forever to draw on here so it doesn't glitch. Okay, now we have to figure out the LCM. So what is the maximum amount that you have in each? So the maximum amount of 2's I've got is 1, 2. So my LCM, I need to use 1, 2 That's the maximum amount of 2's. How many 3's do you see? 2. I need to take the most amount. So I'm going to use both 3's. Times 3 times 3. All right, I've used the 3's. How many 7's do you see? 1. So I got to use the 7. How many 11's do you see in each number? In each number? No, there's 1 in each number. Times 11. And that's going to be a huge number. It's going to be a 4-digit number. We're going to get 1386. Okay, so again, where did most of these numbers come from? We're taking the maximum amount for each value. It's not giving it to me. All right, we're going to move to a perfect squares. How do they change when we're doing perfect squares? They don't change very much. So we know that our perfect squares for our first list going 1 to 7 would be 1, 2 squared is 4, 3 squared is 9, etc. Every square has possible 2 square roots. For example, if I go square root 9, well, that could be equal to negative 3 times negative 3, or positive 3 times positive 3. The positive one is considered the primary, okay? And which we call the principal square root. So that's always the positive one. So that's this guy. The positive square root is always called the principal one. So think of the principal of your school. The principal, the biggest, the one that makes all the rules. So the biggest one there, that's going to be the positive. Now, the negative one is called your secondary root. Do we use them often? Yes. But one thing we have to remember is, if I write this down and I say, what is, I need color. If I said to you, what is the square root, come on now, of 25? And it was a true-false question. And if I said A, 5, B, I might say negative 5 and positive 5. C might be negative 5. The answer is A. Whenever we answer any question with square roots, they're always wanting the principal one. Yes, we know that a negative times a negative will give us a positive. But if they want the negative square root, what they do is they put the negative sign in front of the square root. So if I said to you this, if I wrote it differently, so if I wrote it like this, square root negative 25, that answer would be C. Okay, negative 5 and 5, that's the theory. We know they do both, but when we're talking in math, which one do we always refer to? The positive one, no matter what. Because if I'm talking about a triangle, and I've got a triangle here, and I said to you, I need to know what the length of this is. And if the length of that is square root 16, you're not going to tell me that it's negative 4. It is a positive number because it has to be a positive number in terms of real life, length, width, height, all of our numbers that we use for measuring, those are always going to be positive. So we're never going to say root 16 equals negative 4 on a triangle. That would be wrong. We would be using the positive principle always. Okay? So you have to recognize that because you're going to get multiple choice questions that ask you this. They're going to say, what is the answer of square root 25? You'd have to tell me 5. Yes, we know it's both, but unless they put the negative out front, you ignore the negative one. Okay? So that's one of the rules that we have to think of. All right, back to what this is talking about. So it says the principal square root of the numbers above, principal ones meaning the positive ones. It says we are only dealing with whole numbers. So that means we're only going to be dealing with the positive ones. When we start dealing with the negative ones, that means we're dealing with integrals and integers, And then when we start dealing with fraction exponents and stuff, and fractions under root signs, that's rationals. Okay, we're going to get there. We're just not there yet. All right, so we're going to fill out what each of these numbers break down into. We know that 3 multiplies by another 3 to give us 9. We know that 36 can divide by 4 and 9. 4 will break down into 2 times 2 and 3 times 3 for number 9. So now I get 2 times 2 times 3 times 3. Okay. The square root of 49, we break it down, we're going to get 7 times 7. And 7 will not break down. So 49 is 7 and 7. Whoops, I got to put a times sign in there. The square root of 49 is 7. Square root of 36 is 6. 2 times 3. Square root of 9 is 3. And 64, we're going to get 8 and 8. But what does 8 break down to? 8 breaks down into 2 times 4. 2 times 4. And the 4s break down into 2 and 2. We're going to get a lot of 2s here. We don't need that line there. Okay. So now we're going to break this guy down. If I take a look, you got to count all them little baby 2s. So I've got 1, 2, 3, 4, 5, 6 2s. So now I'm going to draw 6 2s. 2. Now, we can also call this, instead of writing it this way, I can say 2 to the 6th equals 64. I can use my exponents and powers. That 6 there is telling me I've got 6 2s. That's what that's telling me. I'm using 6 number 2s. And what we're going to notice is the prime factorization of any perfect square will always involve pairs of the same number. Okay, so the same number is going to show up in pairs. So when I take a look at the 49, 7s, there's 2 of them. That's a pair. If I look at 36, I have 2 2s and 2 3s. I have a pair of 2s and a pair of 3s. Okay, so they're always going to come down in pairs. So let's take a look at the next question. Here is a huge number on the next page, really big number. It says, use the calculator to find the square root of this guy. Well, if we use it on our calculator, we're going to get the number 210. Now we want to find prime factorization. So, if it is a perfect square, that means all the factors must be in pairs. So I'm just going to write a note here. I'm looking. Oh my gosh, that does not say looking. Wow. Unreal. Okay. I'm looking for pairs. Pairs of factors. If that would say it. Okay. I'm looking for pairs of factors. So the first thing I know, it ends in 2 zeros. If I know something ends in 2 zeros, it's going to divide by 100. So that means if I do a tree diagram, I'm going to have the number 100 here. And that would be 441. And now if I square root 100, 100 I know breaks down into 10 times 10. So now I've got my two pairs, or one pair, I should say. 441, I think, breaks down into 21. Let's check it out. Yeah, he breaks down into 21. So this guy has a pair of 21s. Now, each of those numbers can break down. And when they break down, they're going to break down into pairs again. So when I break down a 10, it's going to break down into 2 and 5. And this 10 is going to break down into 2 and 5. So I have 2 2s and 2 5s. So far, 441 with a couple zeros at the end, so far looks like this. 2 times 2 times 5 times 5. That's what we've got from the 10s. Okay, that's my 10s. Now I'm going to deal with the 441. That's 21s. So now I'm going to break these guys down. 3 times 7. Oh, I guess I don't need to write the times sign in this diagram. And the other 21 will break down into the exact same thing, 3 and 7. So now I can add those to the end. Now the 3s are going to scooch in between the 2s and 5s. So the 3s are going to come sit in between there. So times 3, times 3, times 7, times 7. All right, that's what it breaks down into. Now I want to know, since it's the pairs, if I want to know what the square root of 441, 0, 0 is, I use one of each of the pairs. So I'm going to write a note. Use one of each pair. And that's to get the square root. So now I'm going to use one of each. So I'm going to use 1 2 and 1 5 and 1 3 and 1 7. And that would show us 2 1 0, 210. Holy glitch. Stop it, go down. 2 1 0. There we go. Alrighty. Oh crap. As we can see, we had to choose whether or not 1225 or 3042 is going to be a perfect square. If they break down into doubles, yes, they are. So we notice on the left, 1225 broke down into 2 doubles. So yes, it's a perfect square. On the right, we have doubles for 3s and doubles for 13s, but we have a single 2. So that single 2 makes this guy not a perfect square. Moving on to perfect cubes, we're going to break down 27. Has a 9 that breaks down into a 3 and a 3. So if it's a perfect cube, the number occurs in triples. Okay, so the number, your factor, occurs. If I'm writing, you're writing, that means it's important. Occurs in triples. And we can see that 27 ends up with 3 3s. So we would say yes, 27 is a perfect cube. Let's take a look at 216. 216 is even, so he's going to divide by 2. And that's going to give us, 108. 108 is also even. We're going to divide by 2 and get 54. 54 is also even. We're going to divide by 2 and get 27. And 27 we see there divides by 3 and 9. And 9 ends up with 3 and 3. So I need triples of my factors. Do I have 3 2s? Yep. Do I have 3 3s? Yes. So that means 216 is, yes, a perfect cube. Okay, because everything's showing up in triples in my final answer. So my final answer, I have 3 2s and I've got 3 3s. Okay, and that's how I know. 3375. The number ends in a 5.
Well, I was going to say, how do you, how do you find what the cube root is?
On the calculator?
No, just by this.
Just by this?
You could do
the cube root would be each small number multiplied by each number. So for example, here, the cube root of 27 is just 3. It's whatever number shows up in triples. So on the 27, the number that showed up in triples was a 3. So we'd say the cube root of 27 is 3. And now if I said to you the cube root of 216, it'd be 2 times 3. Exactly. Because there's 2 of them. I have triples of 2s and triples of 3s. So it'd be 2 times 3, which is 6. And if you go on your calculator and go cube root 216, it'll be 6. Okay? Same thing's going to happen for 3375. We can throw it in our calculators. We can figure out the answer's going to be, but what's it going to look like? Well, we divide by 5 to begin with. Then we're going to get a 675. Then that guy divides by 5 because he ends in a 5. And that's going to give us 135, who also ends in a 5. So he'll divide by 5 to give us 27. And we know the number 27 is a perfect cube. He'll break down into 3 times 3 times 3 because he'll break down into 3 and 9. And the 9 breaks down into 3 and 3. So I need to write down my triples for this guy. So my triples for this one, if I said cube root of 3375, it's going to be, I have 3 5s and 3 3s. So it's going to be 5 times 3, which is 15. And now we can go on our calculators and confirm it. So on your calculator, you're going to hit Math 4. Math 4 is going to bring up your cube root sign. And then you're going to type in the number 216 equals. Okay, so off to my calculator, math, hit my math button, 4. There's my cube root. I go 216, enter. I'm going to get 6. Then I'm going to do the same thing, math 4. And I'm going to put in 3375. And it's going to bring up, whoops, wrong order, 7, then 5. It's going to bring up the number 15. Okay, so we can figure it out longhand, and then we can put it in our calculators to confirm that we got the answer correct. Okay? Any questions on prime factorizing a cube or a perfect square? Let's take a look at the next page with last 2 examples. Come on, button. All right, the prime factorization of a perfect cube involves sets of factors that occur in 3s or triples, and for a perfect square, it occurs in doubles. So it says, if the number does not result, then it is not a perfect cube. So just like that last question, it didn't, or the previous questions, we were looking for pairs in the perfect squares. One of the questions didn't have a pair. So we're going to do the same thing here. These are large numbers, so we're going to use division tables. So I'm going to start with the number 2. And the reason I'm starting with the number 2 is because it's an even number. So that's going to give me 3456, which is also even. So I'll divide by 2 again to give me 1728. And I'll divide by 2 again to give me 864. Again, an even number. I'm getting lots of 2s here. That's going to give me 432. And I'm going to get an even number. And that's going to give me 216. And what do we know about 216? He's a perfect cube. So 216 is even. He'll divide by 2 to give us 108. Divide by 2 to give us 54. Divide by 2 again to give us 27, which is odd. So it divides by 3 to get 9, which divides by 3 to give us 3, and then 3 to give us a 1. And now we got to check and see if we've got triples of our numbers. So I need to have numbers that occur in triples. So let's take a look how many 2s I've got. Okay, if we're going to color those guys, how many 2s do I have? I know I've got 3 3s. I need 3 of them to be a perfect cube. But let's count the 2s. I've got 1, 2, 3, 4, 5, 6, 7, 8. Is there enough 2s? No. Because I have 3 right here, 3 right here, and this guy is missing a 2. Okay, I would need 1 more 2 for it to be a perfect cube. So this guy is not a perfect cube. Okay, so that guy's not a perfect cube. We're going to do the same thing with the next one, and we're going to see if he is a perfect cube. And that'll be it. So again, it's a long, big number, so we're going to use a division table. He's an odd number, so I'm going to start with the number 3, and 3 does work. That's going to give me 323 and 433 at the back end. Again, it ends in a 3, so I'm going to divide by 3. 107, 811. It's an odd number, so I'm going to divide by 3. And that gives me 35, 937. Again, an odd number. Always check 3. If 3 doesn't work, go to 7. Why wouldn't you check 5? Because it doesn't end in a 5. Good. So this guy does divide by 3 to give us an 11,979. That guy ends in an odd number. We're going to divide it by 3 to give us 3993, which will definitely divide by 3s to give us 1331. And now that guy, we're going to go divide 3. Didn't work. Divide 7. Didn't work. Divide 9. Doesn't work. Divide 11. So this guy now is going to divide 11. And we're going to get 121. And again, 121, we're going to check. Does he divide by anything? Only 11. Because he's a perfect square. 11 and 11. And 11 divides by 11 to give me a 1. So now I got to see if my numbers occurred in triples. So this guy's a triple. There's 3 of those, 3 of those, and 3 of those. So, oh, it froze again. Okay, well, I'm showing you, go from the 121 where it froze. It's going to make 11 and 11, and 11 will divide by 11. So that means this guy is, yes, a perfect square. So you can write, yes, he's a perfect square. Or, sorry, perfect cube. He's a perfect cube because all of his factors occurred in triples. His prime factors occurred in triples. Okay, that is the end of lesson 2. You've got the rest of the block to finish lesson 2 in your workbook. Tomorrow we will move on to lesson 3.